So today we're very happy to have Minjae Cho from the Princeton Center for Theoretical Science at Princeton, who's going to tell us about positivity applied to the Ising model on the lattice. So Minjae, please take it away.
Thanks, Bruno. Thank you for giving me the opportunity to speak here. I'm glad in particular because I'm giving a talk at a center named after a great physicist whose work is much relevant to the topic of today's talk, which is Ising model on the lattice. So when I say Ising model on the lattice, it's the good old Ising model that we learn in statistical mechanics. It's such an old model that when I say something like, I'm going to give a talk on this, very expectation is that I'm not going to tell you about completely new physics, rather it's going to be about a new approach to study such a system. And the name of such an approach is positivity. And this is based on this preprint, which I worked on together with my collaborators here, different people in Harvard and Princeton. So typically, motivation part of a talk involves some general statements, but I think for this talk, it's more suitable to motivate by considering toy example. Okay, so consider a function of one real variable x, okay, f of x, and we are going to define its expectation value in the following way. So in short, we have measure factor, which is given by this exponential factor. This is the Gaussian term, but there's also x4th term. Okay. So if you wish, this is 0 plus 0 dimensional phi 4 theory. And the question is, how do we evaluate something like x squared expectation value? Well, of course, if you just plug this into Mathematica, it's gonna spit out some 2f1 or Bessel function. But say you don't know about that, okay, and you want to get a number for this type of thing. Well, Mathematica can again deal with such a thing. There's a very beautiful function named n-integrate. This is what's doing the numerical integration for this type of expressions. So if you look into details of this, what this is actually doing in practice, you're going to find something on the right-hand side. So it's going to sample over some values of x, okay? And Mathematica recognizes that the value is actually bigger around this area and this area, and it's very small around the infinities. So it's going to do more and more sampling around this big area, these areas where you have big values, and it's going to take Riemannian sum. Okay, so it gives some estimate for this type of integral. Well, of course, if there was the end of the story, I'm not going to give a talk on this. The option is that there's now a second answer, which is also given by Mathematica, and it's called SDP, which is shorthand for semi-definite programming. And in order to use this, we actually have to write down 2 more lines of code. Okay, for n-integrate, you just plug in this expression into n-integrate. For SDP, you need to write down 2 more lines of code. The first line has to do with something called relation. Okay, it's a simple statement that if you evaluate total derivative under this integral, you're gonna get 0. By the way, here I'm assuming Z2 symmetry, so I'm setting all the odd moments to be 0. So we have only the even powers to consider. Well, okay, once you take this expression and just write it out, you're gonna get this type of expression. Okay, and you can see that this is a recurrence relation between different powers of x. Of course, the 0th power is normalized to be 1. And what it's saying is that basically x squared expectation value determines all the other moments. In particular, notice that this relation is linear in the expectation values. And this is going to be important. Any question on this one? Good. So the second line that you have to add to Mathematica is positivity. Okay. And it's again very simple statement that take any real polynomial of x. Okay. So these coefficients ck are all real. Once you take square of it and take expectation value, it is positive. Why? This expression itself is positive, and the measure is also positive. Any question on this one? Now you notice that because this thing holds for arbitrary choice of coefficient ck, this can be equivalently written as semi-definiteness of the following matrix. So we are going to define a matrix M whose ijth element is given by the expectation value of the x to the I plus jth power. Okay. Then it's straightforward to see that this positivity is equivalent to the positive semi-definiteness of this matrix M. If you wish, and if you write out the explicit matrix elements, this is how it looks like. Of course, this statement on its own is a almost void statement. It doesn't tell you much. But now, the upshot is that, okay, we know that all these odd moments are to be set to be 0. And we know that x4, x6, x8, and all of those things are going to be written as a function of x squared. And one thing to notice here is that these matrix elements are linear in this expectation value. And that's going to be helpful in practice. Okay, we've written down the 2 extra lines to the Mathematica, and the end result is the following. So we have this M matrix. It now depends only on x squared once you plug in the relations. Okay, and this is how it looks like. So you have a matrix which is linear in the x squared, and this M0 and M2 are some constant coefficients. And we have the statement that this matrix must be positive. Now you might wonder how you want to use this type of positivity, and you bring this problem to your friend who knows something about optimization, and your friend will directly tell you, oh, this is one of the easiest problems. It's called SDP. So here's a statement of SDP problem, semi-definite programming in this context. It's like the following. Find the minimum or maximum of this x squared subject to this positivity constraint. Any questions so far?
The outcome of this procedure would be some inequality, whereas the outcome of an integrate is closer to an equality.
Well, that's only an estimate because you took a discrete sum. While the bounds you get from this one is rigorous.
That's true, but sampling more discrete sum. But this is an open condition versus a closed condition. So it seems comparing them seems somewhat not the same. But this is an inequality. At best, this is going to converge to a rigorous inequality, but you may be very far from saturating this inequality.
Okay, let's see what we get. So I told you, you can write this down in Mathematica. I told you that you have to write down 2 extra lines. First line is a relation, which I already explained. Second line is a matrix. By the way, in practice, you have to, this matrix M is infinite dimensional matrix, but you have to consider some, principal submatrix of it. But still, the bounds you're gonna get are rigorous. As you consider bigger and bigger submatrix, it's only going to give you better bounds. Okay. So we consider the first 20-degree polynomial. And then this is the mean. So here, there's a fancy function in Mathematica called semi-definite optimization. It was introduced in Mathematica 2019, and it's built-in function. And when a function is built in Mathematica, I think it's fair to call it a very standard function. So you can take this just as something that's as standard as an integrate. So this is mean, this is max, these are the results. They differ only around 8th or 9th digit. The exact result is below. How long does it take to get these numbers? Instantaneous. I can give you this code if you want. Okay. But again, these are rigorous bounds.
Could you say a bit about how the truncation error depends upon the rank of the matrix you consider?
Oh, sure. Of course, if you consider just first 1 by 1, it's going to be trivial. It's not going to give you any bound. If you consider 2 by 2, it's going to tell you that this is bounded above by 1. Okay. So you see that you have to increase it in order to get something better and better.
But it's inverse poly in the rank or inverse exponential or something?
I didn't attempt doing the estimation for that. But as you can see, already at 20 by 20, you get highly precise result.
But that seems like an accident. I don't understand why is it converging the upper and lower bound? In general, inequalities do not converge. Why
Well,
is
in a
there
sense-
an open set?
In a sense, you used everything you know about the system. The relations
No, we didn't.
are, in a sense, like the equations of motions. Okay, you used all possible equations of motions up to some, power. Of course, you might ask, why does bootstrap work well? That actually applies to any bootstrap setup. And there are only a handful, examples where we understand the reason why. But let me take a practitioner's approach.
But for some very simple system, we understand that some inequalities might saturate. But in general, inequalities are not saturated. I'm confused why you think that this is equivalent to just doing the integral. I still don't understand why you're.
I didn't say that it's equivalent to doing the integral. This is putting rigorous upper and lower bounds. Whether you get highly precise bounds or not is, of course, it may depend on the specifics of the problem at hand. But here I'm only demonstrating the idea. Yeah, and later when we go to Ising model, so n integrate is like the Monte Carlo. This one, there's going to be a suitable generalization of this story to Ising model. And you'll see how this inequality or positivity approach beats Monte Carlo by a lot.
Does the bound, do the upper and lower bounds like converge to the true value as you increase the size of the matrix that you're considering? Or do they converge to?
In practice, that's what we see in this example. But of course, coming up with some, rigorous explanation for such a convergence is out of the scope of the talk.
Okay.
Yeah, here I'm just demonstrating it.
I mean, in SVP, there is this idea that if you have a dual program, then convergence would imply that they would converge to the same answer. Is there some sort of dual STP for this?
I think basically the algorithm that this STP is taking is basically primal dual procedure.
I see.
So it's primal feasible and also dual feasible. But I think that is different from this min and max separately converging to each other. Yeah, that is for the convergence of this single value when you run the STP.
I see. But this min and max ones are not in some sense dual to each other.
No,
Okay.
they're not.
Thanks.
Thanks for all the questions. So at least I think the TOEIC example was motivating enough. Any questions so far? So now let's move on to some list of stuffs, okay? So I told you about how positivity combined with relation may prove to be very powerful. And of course, in our field, in high energy theory community, there is a prototype example of it by now, which is numerical conformal bootstrap, which is highly precise and which is one of the best examples of such a thing. But let me consider other cases in literature. As far as I'm aware of, the very first approach along this line in the set of a quantum mechanical system was actually done in the quantum chemistry by these people, and I'm glad that David Masiotti is actually here. For people who don't know him, he's faculty here at chemistry department, and he's worked a lot on this thing. So there, the objective is to get the ground state energy of some n electron system, and you can consider the 2 electron reduced density matrix and impose positivity constraint on it. And that actually led to highly precise determination of the ground state, even though one gets just the lower bounds, but they actually converge to something expected. And there's also another setup where this type of approach, positivity and relation, has proven very powerful. That's in the context of classical dynamical systems. And this was initiated in work by Boluskin, Fantuzzi, and other collaborators in 2015. And if I have time after the talk, I might actually present you a few slides on this because I'm currently also working on this one. In high energy theory community, there have been several works along this direction. The earliest one, which I'm aware of, is this large and lattice gauge theory by Anderson and Kruchansky. So they consider the strictly infinite n and lattice Yang-Mills, pure Yang-Mills, and then they write down the basically positivity is the reflection positivity, and relation is given by the loop equations at the leading order in 1/n. And that actually had major improvement by Kazakov and Zhang early this year. And they prove highly non-trivial upper and lower bounds on the plaquet expectation value. Of course, there's by now a classic work by Henry Lin in the context of large matrix interval, which soon got generalized to all these matrix quantum mechanics. And over the past 2 years, there have been plethora of quantum mechanical bootstrap papers. I simply couldn't write all of them down here. But I wish to point out this work in particular. So this Nepal and Shin work, which was published early this month, actually takes into account something analogous to crossing in numerical conformal bootstrap. And I would say that their work now puts quantum mechanical bootstrap on the same level as the numerical conformal bootstrap. It's a beautiful paper, which I recommend you to read if you haven't done so already. And today, I'm going to add to this list the case of statistical mechanics. Okay.
And Carol was an undergraduate.
Oh, really? I see. I mean, their work was beautiful. Yeah. Okay, so I'm going to tell you about Ising model on infinite cubic lattice. By infinite, I literally mean the infinite lattice. Okay, I'm not taking any boundary condition or anything like that. By cubic, I mean hypercube. So this can be square in 2D, it's cube in 3D, and 4 cube and blah, blah, blah on all the higher D. So the lattice we have, lambda, is integer linear combination of unit vectors. So this E mu are unit vector along muth direction. Okay? And we are taking the integer combinations. So in 2D, this is how it looks like. We have E1 and E2. And on each lattice side, we are going to have a variable, which is denoted as this S of X. Okay? So this is spin variable, and you can take discrete values plus or minus 1. Just like in the single integral toy example, we are going to have this measure factor now. Okay? So in that case, the measure factor was e to the minus x squared minus x fourth. In this case, we have this measure factor. The first term is nearest neighbor interaction. So this spin sum is only over the nearest neighbors. The second term is something called external magnetic field term, which is now summing over all the spin insertions. Okay. So this is good old Ising model, which is a prototype of ferromagnetism. And by ferromagnet, I mean this J is going to be taken to be positive, and H is also going to be taken to be positive, which is a traceable convention. Any question up to this point? Okay. This is the good old Ising model we learned in STEM course. So what are the observables of interest? They are the spin correlators. In order to define them, let me introduce one more notation. So say we are given some subset A, finite subset A of this lattice lambda. Okay? By S underbar A, what I mean is product of the spin variables which are located at this subset. Okay? So for example, if our subset composes of these 3 sides, origin, E1 and E1 plus E2, which are like this, then by S underbar A, I mean just product of the spin variables there. Okay? And this is the main character of today's talk. We are going to take expectation value of this spin configuration, which is defined as the following. We normalize by 1 over Z. On the right-hand side, we have this thing as inserted, together with this measure factor. And we are summing over all configurations. By the way, because I'm on infinite cubic lattice, I have, in addition to the rotation and basically dihedral group symmetry, we also have translation symmetry. And when we say we have a symmetry, it means that spin configurations related by symmetries realize same expectation value. So here we have S origin and SE1. If we rotate it, we have S origin and SE2. Those have the same correlator value. But if we translate this here like this, they are also the same. So I'm going to always assume this, meaning that I'm, for example, not considering the finite lattice with some Neumann or Dirichlet boundary. for your Dirichlet boundary. Okay, the point is the following. So, I'm using the same notation as in the toy example case. It's because this is essentially the same problem, okay? In the toy example case, we had only one variable, x. Now we have infinitely many variables, one per each side, which take discrete values, but you can just imagine that they are, delta function supported. And we have some positive measure. Okay? So this is just toy model now with infinitely many integration variables and positive measure. Is this point clear? So this means that we can run the same machinery of positivity and relation to study this system. Any questions so far? So what's the relation now? So in the toy example, we got the relation from the fact that total derivative integrates to 0. But that can be equivalently derived by considering infinitesimal change of the integration variable. Okay. So here, we are going to take change of variable for this sum n. So fix a point P in the lattice. And we are going to take change of summation variable SP to minus SP in this sum. Okay. Under this change, this correlator should remain the same. Why? Because we just redefined the summation variable, which is a dummy variable. Of course, your left-hand side is whatever it is, but as you take the change here, on the right-hand side, you're gonna get something that seemingly is different. And that's where the relation comes from. So what's going to change? So first of all, this integrand, in a sense, changes sign if this subset A includes the point P. If not, it doesn't change sign. Let's look at this magnetic field term. Now, because we changed the sign of SP, it's going to change to this one, or equivalent to this one. And similarly for the nearest neighbor interaction. So upon taking into account all these changes, this is what we have. And this relation is named spin flip equation. So this left-hand side should equal this right-hand side. Okay? They look different, but they must be the same. If you wish, this is analog of Schwinger-Dyson equation, loop equation, or whatever you name, equations of motion. You might say that, okay, at least we want this equation to close. Well, on the left-hand side, we have polynomials in the spin variables, while on the right-hand side, we have exponential. But that's too quick. We know that all these spin variables, they square to 1. So as you Taylor expand this exponent, you're actually gonna get only finite degree polynomial in terms of the spin variables. So for example, let's look at this magnetic field term. We have e to the minus 2h times sp. As you Taylor expand, it's gonna truncate at the linear term, in the linear term in sp, because it squares to 1. Okay. And nearest neighbor interaction term is a bit more complicated, but after some exercise, you can actually make sure that this expansion is again going to terminate at some finite degree in terms of the spin variables. Any questions so far? By the way, we are not the first one to derive this one. These were already known in the 60s. Okay. So these are very old results, which are not very much used somehow. So let me give you an example. So this is for the square case. And let's set external magnetic field to be 0. And you notice this spin flip equation exists for each choice of subset A and the spin flip P. Okay, for each of those choices, you have this equation. Okay, so in this example, we are going to choose P to be the origin and the subset A to be the empty set. Okay, so on the left-hand side, we just have 1. Okay, 1 is equal to something. Once you write everything out, this is the expression you get. So here, A and B's are some coefficients, some numbers which depend on the coupling J. But you see, there are all these spin correlators. Okay. By the way, I already made use of the symmetry in writing this. And you can see that not all these spin correlators, which seemingly look different, are independent of each other. They should satisfy this linear equation. Okay. So let me give you some idea about the counting. Okay. So in 2D case, we considered something we call 13531 diamond. Okay, why diamond? So look at this inner green diamond. This is 131 diamond. If we take a spin flip at any of these, any of these locations, because of nearest neighbor interaction, its spin correlator is going to involve something that's stretching by one side, following its neighbors. Okay, so for that reason, we are going to take spin flip within this inner diamond. And then for this choice of A, we are going to take all possible spin configurations in the bigger diamond. Okay. So we are going to make all possible choice of P and A within this diamond. Everything clear? So in non-zero external magnetic field case, to begin with, you might say there are 2 to 13 possible spin configurations within this 13-side diamond. Okay. After using symmetry, it reduces down to something of order 1000. But once you write out all possible spin flip equations within this domain, you find that the number of them are again of order 1000. In the end, you're going to end up with only 29 independent spin correlators. Okay. So this is huge reduction in the number of variables. And similarly, in 3D, we consider this type of diamonds. This is 15551. This is 15551. And in the last case, for example, by the way, when we have external magnetic field set to be 0, these numbers are based on the assumption that all the odd powers of spinning correlators are 0 by Z2 symmetry. So after that, the counting looks something like this. So the option is that naively there may seem to be a lot of independent spin correlators, but after using spin flip equations, there are only a handful of them remaining. And let me make the point that even though I'm considering here some finite domain, the result we are getting here is strictly rigorous for the infinite lattice. I didn't take any assumption about the finiteness of lattice or anything like that. Okay. Any question? Good. Now we have second character of the method, which is positivity. Okay. Let me start with the most naive one, which is something called square positivity. This is very simple. So take O, which is some real linear combination of these spin configurations. Okay. And consider it squared, and then take expectation value. It should be positive. Why? Because O squared is manifestly positive, and the measure is positive. Okay. Empirically, we actually observed that this is implied by other positivities, which are going to be discussed. So you may as well forget about them from now on. The second types of positivities are something known as Griffiths inequalities. You can find introduction to these inequalities in the classic textbook by Glim and Jeffy, for example. There are actually infinitely many such inequalities, but I'm going to tell you about only the first two. So G1 is the first Griffiths inequality, and it's just saying that in the ferromagnetic case, all these spin correlators are positive. How do you prove it? It's actually easy to prove once you express this from the perspective of zero coupling theory. Okay. In the zero coupling theory, basically you have to now also evaluate this measure factor. But because we're in the zero coupling, this expectation value is going to be non-zero only if you have no insertion of the spin in this expression. And because J and H are positive, you're going to only get a positive thing once you Taylor expand this and get the terms which are independent of the spin variables. Second Griffiths inequality is a bit, it requires more steps to prove it. I'm not going to provide you with the proof. But it's roughly the following statement. Consider A and B, which are subsets in your lattice. First, you take their product and then take expectation value. Second, you take expectation value of each of them and take the product. Second Griffiths inequality tells you that the former is greater than or equal to the latter. Notice that this inequality is actually non-convex in the spin correlators. And for that reason, we are not going to impose them when we are imposing all the positivity constraints. But later we are going to see when it backfires to us. And finally, the third positivity is reflection positivity. It's not surprising that reflection positivity comes on because, that's the typically only positivity we have in any unitary Euclidean quantum field theory. So I'm displaying here 3 reflections in the 2-dimension case. But it turns out that even in higher dimensions, there are no other types of reflections. So it suffices to draw just things on the square. You can simply replace reflection axis by reflection planes or hyperplanes in the hierarchy. So first reflection is reflection along the vertical side. Okay, this red dotted line is a reflection axis. So in the left half space, which in particular includes the axis itself, if you have spin configuration like this, green dots, upon reflection, you get this blue dots. Second reflection is vertical reflection, but along the links. Okay. And finally, the third reflection is diagonal on-site reflection. So if you have these green dots, they reflect to these blue dots. So what is positive about these reflections? Well, it's something natural to write down. So here, I'm going to tell you the story only for the first reflection. Okay, the story for the second and third reflections are essentially the same, similar. So in this first reflection, again, the reflection axis is along this vertical on-site line, which I'm going to call P. And I'm going to call left half space as this H, which in particular includes P. Okay. And I'm going to consider spin correlators, which are real linear combinations of spin insertions only along the left half. Okay. So we are considering spin insertions only only in the left half space, and its reflection is defined in the following. We take the same coefficients, but for the spin variables, we are going to take the reflected ones. Okay. And now the claim is that if you take product of these 2 things and take the expectation value, it is positive for any real coefficients. Is the statement clear? Proof is actually very simple. It can be written in 2 lines. So we are, in this expectation value, we are taking sum over spins. So let's pull out the sum over this reflection axis P. Okay. I pulled it out. And in particular, I also pulled out the measure factor, which depends only on this P. And everything is positive here. Now, let's imagine that we are doing the sum over the left half spin variables. Okay. But now, we are not going to take into account the spins over P. We are going to only take the sum over this half space minus P. Whatever that value is, there's going to be some function of spin variables only along this reflection axis because of the nearest neighbor interaction term. Okay. And that function I'm going to call psi of S underbar P. What about the right half? You can do the same thing. But the thing is that because right half is defined simply by the reflection of the left half, you're going to get the same function psi of SP. So you have psi of SP squared. Okay? You have squared thing times positive thing, and you sum over that, you have positive thing. Is everything clear? Any questions so far?
So what,
Here we've relaxed the restriction that J, the nearest neighbor interaction, has to be positive, or is it still present?
Oh, good. So here you can relax it.
Yeah.
Actually, for this second reflection, you actually need J to be positive.
When you do the analysis, will you impose it or not?
Oh, we actually impose it. So we impose also this reflection positivity. Thanks for the question. Yeah. Any other questions? Oh, by the way, of course, we are not the first one to prove this thing. I mean, this was proven all the way back in the 60s. So all the ingredients that I introduced here were already there in the old literature, but somehow people didn't combine them. So all we did was to combine them. I mean, of course, in the 60s, there was no SDP. That was the main difference. Okay, we have positivity and relation, and we can run the same procedure as in the toy example. So spin-flip equation tells us that any spin correlator that we are going to consider is expressible as linear combination of some independent spin correlators. Okay, if you recall, in this diamond case, there were about 2 to the 13 of these guys. But using symmetry and spin-flip equation, there were only like 29 of these guys. Okay. And these coefficients are something that's dictated by the spin-flip equations. And we have reflection positivity. There are, again, 3 reflections. And as I should have mentioned this. So, okay, this positivity, again, can be written equivalently as positivity of the following matrix. So here the matrix carries indices which are now subsets in the half space. And the matrix element takes this half space configuration times the half space configuration reflected. Okay. And this matrix must be a positive standard. Okay, so we have 3 types of such reflection positivities, which are now expressible in terms of these independent spin correlators only. Okay. And notice that these are all linear. That's going to be essential for the practical implementation. And finally, there was another linear relation given by this, first Griffiths inequality, which can again be expressed in terms of the independent correlators. Now we minimize or maximize some correlator of interest subject to this positivity constraint. It's exactly the same strategy we used for the toy example. Okay, any question before I jump into the results? Good. So first thing first, in 2D, in the absence of external magnetic field, there is analytically known solution. Okay. So for example, let's take the nearest neighbor spin correlator. And x-axis is the J, the coupling. And this black line is the analytic solution. The gray dots, which might be a bit hard to see, they are the upper and lower bounds coming from the 131 diamond. As you increase the diamond size by basically 1 unit, you get these blue dots as upper and lower bounds. And you can see that it's pretty quickly approaching the exact answer. And it will not be surprising if you consider the next, diamond. Probably human eyes cannot distinguish between the exact answer and the bounds. And again, these bounds are rigorous. They are rigorous for infinite lattice. And this is the bound for next to nearest neighbor interaction. Spin correlator. And it's still pretty good. You can see that the bounds are actually the weakest around the critical point. So famously in Ising model, you have critical temperature, which is associated with the spontaneous magnetization. And it kind of makes sense because at criticality, you have divergent correlation length. So, but on the other hand, we considered spin, positivity and equations only among some finite domain. So it's not surprising that the bound is weakest around here. As you can see, it's gonna probably get very good as you increase the size of the diamond. Okay. So let's compare with another approach to this type of model, which is Monte Carlo. Okay, so here we are using the good old Metropolis algorithm. So here, this is y-axis is a discrepancy. between either the exacting and upper or lower bound, or the 1 sigma error bar, size of the 1 sigma error bar in the Monte Carlo. So this green and blue are the positivity bounds, size of the positivity bounds, roughly speaking. While this orange and red are the 1 sigma error bar of Monte Carlo. As you can see, they are pretty comparable to each other. And as you go away from the criticality, bootstrap is actually, positivity approach is actually getting better. As I already mentioned, one phenomenal feature about this model is that there is a critical coupling. So, of course, the theory itself, in the absence of the external magnetic field, is Z2 symmetric. Okay. But we know that even though it's Z2 symmetric, something like S0, which is odd power in S, can realize something called spontaneous magnetization, some non-zero value, when it's below the critical temperature or above this critical coupling. And this can be actually seen from considering the upper bounds on this type of correlator. And this is the first time where we see the role of the first Griffiths inequality. So firstly, these black circles are the result coming just from the 131 diamond reflection positivities without imposing the first Griffiths inequality. As we impose first Griffiths inequality on top of it, this upper bound actually drops exactly to 0 around here. This is exact 0. One can analytically show that first Griffiths inequality together with the spin flip equation tells you that the upper bound on this value is exactly 0 below here. In a sense, first Griffiths inequality together with the spin flip equation puts the lower bound on the critical coupling. Okay. If we increase the diamond size, well, say we don't impose Griffiths inequality, it actually gets quite good. As you can see here, this is red circle. If you impose on top of it first Griffiths inequality, you get this blue cross. So you see a bit of improvement. But you kind of see that, even if you are not imposing the Griffiths inequality, if you just increase the diamond size, it's gonna converge to the exact value. So this red line is the exact answer. Any questions so far? Good. So now let's move on to the case where we don't know the exact answer. This is for the case of non-zero magnetic field. Okay. So in this case, we don't know the exact answer. So here I am plotting the upper and lower bounds for the nearest neighbor spin correlator as a function of both J and H. Okay. The upper bound is this colored sheet, and lower bound is given by this red grid, which is hardly visible. The reason why it's hardly visible is because it's very close to the upper bound, and this color actually represents how close they are. So the color is in the log scale for the difference between the upper and lower bound. Okay. So for example, around the red area here, the difference between upper and lower bound is something like 0.1. Around the yellow area, the difference is something like 10 to the minus 6. In the blue area, it's below 10 to the minus 15. Okay. And of course, once we go to a high external magnetic field, basically we expect that every spin, every size are going to be roughly independent of each other. So it's not surprising that we are getting this precise bounds. But just the pure numerics around this regime, which is as good as 10 to the minus 6, 7, all the way to minus 15, is bizarre. Let me compare to Monte Carlo again. So in order to visualize it better, I'm looking at the slice where J is equal to J critical. It doesn't have any intrinsic meaning. So this is again the difference in the upper and lower bounds as a function of H. This is the positivity bounds. While the Monte Carlo error, I'm plotting the 1 sigma error bar. Okay. As you can see, as we increase the magnetic field, positivity bounds are performing far better than the Monte Carlo. Actually, if you go and ask your Monte Carlo friend, they will typically tell you that they cannot get more than 6 or 7 digits. But here, positivity bounds are already giving you something like 10 to the minus 15. And it's reverse. Okay. This right plot is a bit hard to understand, but all I want to convey is that you see that sometimes these bars are not crossing this axis at all. Those are the places where Monte Carlo, even with the 1 sigma error bar, lies completely outside of the positivity bounds. Okay? So in a sense, positivity bounds are ruling out Monte Carlo 1 sigma results at several values of h. And if you want to make them complete overlap for all possible values of h, you actually have to include up to 3 sigma. I promised you that I will talk about some role of second Griffiths inequality. And here it is. If you actually look into the bounds, it turns out that the lower bounds are actually not quite monotonic as a function of coupling. Okay? So what does this have to do with the second Griffiths inequality? Well, it turns out that first and second Griffiths inequality together implies monotonicity of spin correlators as a function of the couplings. Okay? But I told you that we didn't impose second Griffiths inequality because it's a non-convex condition. And it is consistent with the fact that we are actually seeing this non-monotonicity. So another way to check this idea is to actually look at the values that you get from the SDP when there are these deep features, non-monotonicity. If you plug those values literally into the second Griffiths inequality, you can see that some of them are explicitly violated. Which is another way of saying that if one can somehow systematically impose second Griffiths inequality, these lower bounds are going to be better, presumably monotonic. And finally, let me present the preliminary result for the 3D case in the zero external magnetic field. So this is preliminary because we didn't try to push the numerics to its extreme. Okay, but it's already pretty good. So these gray dots are coming from the simplest one, which is 151 diamond. And these yellow dots are the bounds coming from 1551 full reflection positivities. And these blue dots, which are the most tight bounds here in the plot, they're coming from 15551. But it turns out that 15551 had matrices which are quite big. So just for the numerical implementation, we took only the leading 100 by 100 principal submatrices. So this result is not coming from the full reflection positivities for this diamond. It's coming from some part of it. So it's already pretty good. And this red line is a Monte Carlo result. Okay. Any questions? Okay, let me share some thoughts with you. So, of course, we want to improve the numerics for larger regions. I mean, so far I've told you about only the, say, nearest neighbor or next to nearest neighbor spin correlators. What about some, long-range correlators, which is going to tell you about things like mass gap and so on? Well, first of all, that would require us to identify something like relevant subset of spin configurations. So even though we are, say we consider very large region, we might want to consider only some, rather than all full possible configurations, some subset of configurations, such that the bounds we obtain from them are still good enough. Actually, when we are writing down all the codes for generating these inputs for the SDP, it turns out that many things were highly redundant. For example, even when we are generating things like spin flip equations, we actually generate much more than what turns out to be the independent spin flip equations. So it means that there are lots of redundancies, and there must be a way to deal with these things more efficiently. So that's what we are currently thinking about. Second thought is about null states. Okay. So consider some reflection positivity matrix. Okay. What if it has an eigenvector with 0 eigenvalue in a rough sense? You might ask me, why do we consider such a case? Well, actually, these are the cases which happen all the time, at least in our setup. So our setup was the following. We run the SDP program. We either maximize or minimize some spin correlator of interest under this positivity condition. Okay? And I mean, it's natural to expect that you're gonna get the solution, this max or min, when this inequality is roughly saturated. And that's exactly when one of the eigenvalues becomes 0. In particular, when we have very tight bounds, it means that these two things are roughly the same. And they are roughly the same as the exact answer, whatever that is.
Why should that happen?
Sorry?
Why should that happen? Why should
Which
M
should
max equal M min? That seems like just hope.
It actually happens once you check the solutions. I mean, whenever you have tight bounds,
That's a
with
definition of
precision,
the
like,
term tight bounds.
I
You
mean,
showed me two sides of a thing, you said maybe they converge, but why would that happen in general?
you know what, we have bounds which are close to each other, like 10 to the minus 15.
Okay, but is that an accent of the system? Is that some feature of the method? It just
I mean,
sounds like
again,
hope right now.
I mean, that's what we see.
No, one place it was 10 to the minus 15, another place it wasn't. I don't know.
Sure. I mean,
Why should I believe that it's going to converge?
I mean,
I have two inequalities. Why should they converge to be both equalities? It seems just like hope.
I mean, okay, if you want to say that that's a hope, I think that's fair. I mean, in this case, we don't have any proof
Is there any
of convergence.
conceptual even intuition why it should happen? Like what if you were trying to convince me over lunch, what would you say? Not a level of proof, but why should it even happen?
Okay, at least for the away from the criticality, we know that we have some finite correlation length. And we are considering some spin equations and the spin configurations in some finite set. When that set, when the size of the subset is big enough to basically contain the correlation length, then you are going to expect good convergence. Is this a good answer?
I still don't understand why the upper and lower bounds would converge to each other though. I understand, yeah,
No. Oh, did you understand my comment?
I guess not.
No, so this is what I'm saying. Say you're, okay, at least in the case of far from the criticality, where our bounds are good,
Okay.
we have short correlation length, right? There's a mass gap. You agree with that?
Mhm.
And basically, if our diamond size under consideration is big enough to contain such correlation length,
Yes.
then the configurations we consider, together with all the equations we put on these configurations, should give a good result. Because it's enough to cover the correlation length.
Meaning that M, why does that relate to M max? That just sounds like I still don't get why that would be related to M max equaling M min.
I mean, you're still asking about why do we expect something like tight bounds?
Yeah. Why? I mean, I understand that this method gives you some nice inequalities, but I don't understand why, in general, maybe outside from a few special examples, you would expect that M max equals M min equals the exact answer.
Well,
That just, I mean, it really just seems like hope.
I mean, it's a hope which is realized.
But I mean, it's also true in the conformal bootstrap that for sufficiently simple systems, there's some kink, there's some feature, they lie on the bound of some inequality, but generic CFTs don't seem to lie on the bound of the inequality.
Okay, I mean, if you have complaint on that, I mean, I think you can complain the same on this. And I'm not saying that, if you consider any generic correlator and generic system and generic coupling, you're always going to get these tight bounds. I'm just showing you the examples where we get tight bounds, and in such cases, we have this. I mean, again, I don't have convergence proof. But again, for some short correlation length system, it seems very natural to have this tight bounds because correlation length is small.
Okay. But then there should be a correlation length correction there.
You're absolutely right. I mean, I'm not being too rigorous about all these things, but I'm just making a suggestion here. when you actually get tight bounds. And indeed, using the solution you get, you can literally check how close these two matrices are. I mean, just element by element, these two matrices are roughly the same. They agree up to like 10 to the minus 8, 9.
Is it because it's somehow equivalent to doing the bootstrap with an infinite system of correlation functions?
Well,
I sort of think that if you were to do the conformal bootstrap where you invoke all operators, then yes, the inequalities would always be saturated.
I mean, okay, if you want to, okay, so.
I mean, in the sense that you're allowing yourself to probe sort of bigger and bigger regions with.
Yeah, so, yeah, that's like considering, just 131 configurations versus 13531 configuration here. So
if I were to try to
more,
mimic what this was in the continuum, would it be considering like bootstrap with more and more operators?
Yeah, for sure. I mean, and in the bigger and bigger regions. Like here, this improvement is, I think, what you're alluding to when you say conformal bootstrap with including more and more operators. That's literally this step, going from this gray dot to blue dot. I mean, yeah, that's what I emphasize again, right? I mean, if you increase this diamond to include more and more spin insertions, I mean, even at the next diamond, these bounds are going to be indistinguishable by human eyes.
Well, we can zoom in, we can change the scale. I mean, I'm not.
Of course, but compared to 1, let's say.
Okay.
Yeah, I mean, your point is fair. I agree that, there are only limited cases where we understand why bootstrap converges well. Yeah, I mean, if you have complaint about that, I don't have much to say.
Well, with regard to your last point about that you didn't maybe yet say about the null state, I mean, this kind of model, won't it have a null state just from the equations of motion?
Oh, great. That's great. So actually, one natural null states are exactly the equations of motion, spin flip equations. Okay. These are actually on top of them. So let me tell you about one possible interpretation of them, even though we don't have any rigor behind it. So, okay, let me go back to this one. So, we now have this type of null state, which means that if you want to define some semi-norm in terms of this reflection matrix, this norm is nearly 0. And by Cauchy-Schwarz, this thing times anything on the other half is also nearly 0. And the way we currently understand them is roughly like the OP relations in unitary Euclidean quantum field theory. Okay, so what are these null states like? So as you can see, it's some linear combination of a whole bunch of spin configurations. As I said, that you have a whole bunch of spin insertions. How can you express that as linear combination of some smaller set of spin configurations? So in that sense, it's something like OPE. But I mean, we don't have any rigorous argument for that, but that's what it looks like. And I mean, one may ask.
Sorry, I'm trying to understand that point. So I thought that like in the continuum, the Ising equation of motion, of course, it is related to the OPE, but it's the phi cubed is a descendant basically. You're saying this is more than that?
This is more than that. It should be related to that. Now, it's really like the OPE. Like we have some, say, I don't know, 30 spin operator insertions. And we are expressing that as linear combination of, say, 29, 28, da, da, da.
But wouldn't a null state be something missing in an OPE? Just having an OPE doesn't sound like a null state to me.
Well, you can always
OPE sounds generic to me.
You can always have an operator times operator expanded in something, take their difference. That's what this null state is about.
But that point of view would suggest that, would you say that therefore every continuum quantum field theory has lots of null states based on that logic?
I mean, of course,
Because there exists an operator product expansion and you can move it to the other side?
and of course, I'm not saying that, so, okay, what do we do with these null states? So a priori, if we want to actually define a norm out of this reflection, we want to modify them, right? So in that sense, they're gone. But when we are actually practically implementing them, we can use this type of Cauchy-Schwarz to actually get more constraints. That was actually my point about this null state. So I'm not saying that, you want to say that there's a whole bunch of null states simply by, subtracting off the OP expansion from the, product of two operators. And all I'm saying here is that maybe they can be used to get more inequalities or relations by Cauchy-Schwarz.
But in principle, the existence of that null state is already in the equality of the two bounds being saturated, right?
Oh, yeah.
So it would just be a repackaging of what you already have.
Not quite. We didn't consider this type of configurations.
Okay, maybe I don't understand. We can talk about that.
Yeah, sure. Okay. Finally, one might ask, can we combine this with some analytic works? Actually, this is suggested by Michael Eisenman and Elliot Lee. I was actually very fortunate because I gave the talk on this topic at PCTS, and these two giants in the field were there, and they were saying that, well, in the 60s, 70s, and 80s, there have been many, analytic works for these type of systems using a whole bunch of inequalities. There are basically infinitely many inequalities. And it's just that most of them are non-convex, just like the second Griffiths inequality. But we know that in the optimization community, people have used a whole bunch of relaxation techniques to relax such non-convex inequalities into convex ones. So what if we apply such a thing, and so on? And I hope that today I conveyed you the message that the combination of positivity and relation may be very powerful. So probably it might be worth thinking about more applications of this approach. There's already a good amount of lists. So I think there are much more to be studied. With that, let me end, and thank you for the attention.
So if you were to try to do the same program for a finite size system, suppose you wanted to make bounds for, I don't know, but let's suppose you did it on like a torus, so you still have maybe the same symmetries. What would be the difference in the program?
Great. So for example, if you have, say, Dirichlet boundary condition, then translation is explicitly broken.
If you have which kind of boundaries?
Dirichlet.
He said
Right.
periodic.
But suppose you did a periodic.
Yeah, so good point. So in the periodic case, actually all the things we considered here apply equivalently, equally to the periodic boundary condition, say on the torus. So what this is saying is that, another way of saying, interpreting the precision of the bound is that if you have power to, say, formulate, I don't know, like 10 by 10 by 10 torus in the 3D, then that's going to be highly precise and good.
I see. So you're saying you would get exactly the same bounds. So I guess what you're saying is, if your diamond is a certain size, it will give you results that are roughly as good, or certainly it can't be better than doing a finite size system that's bigger than the diamond. Is that right?
The bound. So the statement is that if you actually do some torus which is bigger than the size of the diamond,
Yeah.
and that should lie in between the bounds you get.
I see.
Yeah.
And
even though that bound was coming from the smaller diamond.
And conversely, suppose that you happen, maybe this would be not at all sensible, but suppose just hypothetically, you were able to do a diamond that's the same size as your finite size system. Then maybe this kind of is related to Clay's question, then would it be clear that they'd have to converge in that case? Like you have to get exact, if you do a diamond that's exactly the same size as you, it's still not.
It's unclear to me. It's unclear to me. Yeah. But yeah, another way to interpret the precision of all these bounds is really like how good torus can be. But already in, say, 3D, if you want to formulate 10 by 10 by 10, say, torus is, I think it's impossible, at least for now.
These techniques be generalized to imaginary magnetic field?
Ah, great. So that's the thing. So we relied heavily on the reflection positivity, which is basically the unitarity of the theory. In the imaginary magnetic case, we so far didn't weren't able to identify reflection positivity.
What if you just use square positivity? You said that was redundant on the other positivities, but it won't be in this case.
Well, the measure itself is not positive because of the imaginary magnetic field. So you want to come up with some combination
So
such that
there's no notion of positivity in this system.
yeah, but I mean, who knows? One might come up with some combination. I don't know, some combination of the observables such that together with measure you want to impose some positivity, but we haven't succeeded in deriving such a thing so far. But yeah, indeed, that's a very interesting question, and yeah, we were thinking about it for a while at some point, but we don't have much to report on that.
Would you say a bit about the dynamical systems you had in mind for this?
Maybe the people who are interested can stay after.
Yeah,
so that-
yeah, I have 5 more slides on dynamical systems, so I can tell you about that after people are done with asking questions about Ising.
Sorry, just one more quick question. How do you know, is there some heuristic to know that you had sort of all the positivity constraints you need? Like, how do you know that you need reflection positivity in all 3 directions? Or how do you know when to stop? Like to say, I have enough positivity constraints that.
So first of all, a priori, they look independent. The matrices seem different for different positivities.
Right.
But indeed, it's not at all obvious when you have a whole bunch of set of positive matrices, whether some of them are redundant or not. Okay, so that's what I meant when I said that square positivity, for example, seem to be redundant. But we don't have a proof for that. We just empirically saw that that's the case. So I mean, we just considered all possible positivities that we could think of and just impose all of them. But if you ask, are there more positivities to be considered? The answer is yes. For example, here I wrote down MMS inequalities. This actually is a linear inequality. So it's actually subject to the machinery of SDP. We learned about it only recently, so we didn't impose it. So now one can ask, what if we include it? Do we get better bounds? We don't know.
But your belief is with the current bounds, it would converge. So in other words, these other inequalities, imposing them would just speed up the convergence, but it doesn't, you don't need them.
So that's the point here. So this red dot is using just the reflection positivity, while blue cross is reflection positivity together with first Griffiths inequality. You see that there's a slight improvement in the bounds. But when you just compare, how it got better from 131 to 13531, you kind of see that even if you impose just the reflection positivities, if you increase your diamond size big enough, it's gonna converge. So that's actually one of our conjecture, which is that if we consider just the reflection positivities and we consider big enough region, that should probably suffice. That's our expectation, let's say.
So Minjae, just to follow up on that question. So in the case of the second Griffiths inequality, you show that there are some discontinuities that were coming in or some kinks.
Right.
And the conjecture was that, I guess, Jaffe had proven that G1 and G2 inequalities would lead to monotonicity.
Indeed.
So I guess along those lines, do you have like a physical interpretation of what you're missing in the reflection positivity that's coming from the G2? Because you could take your results even without imposing it and just see the violation, and you said you're seeing a violation of G2. Can you interpret that as, I'm missing something?
Good. So actually, if you look into the proof, it's not even using reflection positivity. It's using just first and second Griffiths inequality. And it's actually highly...
The proof for the monotonicity?
Yeah, monotonicity. So actually, if you look into just the reflection positivity, it's very hard to disentangle the amount of information which has to do with monotonicity, I would say. It's highly non-obvious. And
you can't turn around the proof and go from reflection positivity to proof.
Right. Because Griffiths inequalities are by nature different from reflection positivities. But sometimes they have some type of overlap. So, and when on top of that we have spin flip equations, things are even more non-obvious. Yeah. So it's very non-obvious how to disentangle specific information out of some reflection positive matrices or things like that. Yeah. So what do? We just throw in everything we know and get the bound. And actually, from algorithmic perspective, sometimes I think you're probably familiar with this. Like SDP has better convergence when you have some inequalities which are overimposed, like imposed more than once. So that's what's probably secretly happening here, but we didn't try to disentangle.
There are no more questions. Let's thank Minjae again. This is probably recording.
Oh, sure.
Did you have
Sure.